Okay, so in this video, we're going to do some revision about how to do exponential equations. These have been quite well done from probably year 9 for some of you, maybe definitely year 10 for the rest of you. And we're looking at the three different ways, or three main methods of solving exponential equations that you're going to see. One is when you're going to write all the terms with the same base. That's usually the easiest case. Using logarithms, which is not too hard, and the last one is using a substitution. It's kind of like a quadratic in disguise as such. You can't say it's a quadratic, but really it is. So with that in mind, let's go through the three cases with some examples. So this case one is when we're going to have both sides and we're going to write both sides in terms of the same base. So 3 is the simplest base. We're going to leave it as 3 to the power of 2x plus 1. But on the right-hand side, we know 81 is the same thing as 3 to the power of 4. So I'm just going to replace 81 with 3 to the power of 4. And with our index laws, you would then have that power of 4 multiplies the x plus 2. Once you have that, you have both sides with the same base. I can now equate the indices. So we say 2x plus 1 must equal 4 lots of x take 2, and then we have a linear equation to solve from here. So hopefully no real issues from this point. So I'll just finish it off. Equals -9, x would be 9 over 2. This second example is the same thing, except we have 3 terms, but that's okay. That shouldn't worry us. We can do 3 terms. We have our index laws that we know how to use. So we're going to combine all these on the left-hand side and then equate to the right-hand side. So the simplest base we're going to use is 2. So 2 to the x, 4 is 2 squared, and that squared is going to multiply that x take 2 equals, well, 8 is 2 cubed, and that's going to multiply the 2x plus 5. And then we're going to simplify from here. So this left-hand side, when you're multiplying two numbers with the same base, remember you add the powers. So that becomes 2 to the power of x plus 2 lots of x take 2 equals 2 to the power of 3 lots of 2x plus 5. Again, we have the same base each side, so now we can simplify by equating our bases. So I'm going to put them equal to each other. Equals 3 lots of 2x plus 5. Like that. On the left-hand side, we have, if I expand and collect our like terms, you get 2x plus 1x gives you 3x. And 2 times -2 is -4. On the right-hand side, we have 3 times 2x, which is going to be 6x, plus 3 times 5, which is going to give you 15. If I simplify all of this, you're going to have -3x equals 19. But -4 becomes a positive, and then that's going to leave us with x equals -19 over 3. Fractions are okay. I can always check the result if I want to by substituting it back into the start, but I think that should be sufficient for now. This next one is case 2, and this is when you have a single term each side where you can't equate the bases. So for example, with a 5 and 10, I can't write them with the same base. A common mistake is writing 5 squared, but remember 5 squared is 25, not 10. So in this case, we simply need to use logarithms. Now, it doesn't really matter which logarithm you use. The simplest logarithm is to use the same base as the 5. And then when you have that, we can automatically write, instead of a to the x equals y, you then can write it as x equals log base a of y. We need to remember this conversion between the two. So I end up here having the power gets written at the front. So you get 2x minus 3 gets written at the front equals logarithm with the base of the same base we already have, which is a 5, of 10, like that. And then we simplify, also, sorry, solve for x. So we add 3, like that, And then I'm going to remove this so I can actually write. You end up with x equals 3/2 plus 1/2 log base 5 of 10. Hopefully that makes a bit of sense, or at least rings some bells. And do the same thing over here. So again, 12, we can't write that as e to the power of something nicely. So we're going to use, again, a to the x equals y. The equivalent expression for that with logarithms instead is this. So the power comes out the front. You have log base e, which don't forget you can write log base e as ln. So I'll do that from this point on. And you get 3x equals 7 plus ln of 12. That's our natural logarithm, of course. And divided by 3 will give you x equals 7/3 plus 1/3, the natural logarithm of 12. That's our case 2. So those first two cases are pretty straightforward to recognise in terms of the style of equation. It's just the harder part, I guess, is working out whether you can get the base right or not. These numbers are all pretty small. So the 81, the 8, the 4, it's easy to pick their smallest base. It's in common, but sometimes it's a bit harder. This last case is normally the hardest one to pick up, the one that's a quadratic in disguise. Now, the key to this one is anytime you see, usually it's 3 terms you'll see, and anytime the gap between the powers is a 2x, it's going to be quadratic in disguise. Now, what I mean by that is this. If I look at the last term here, you get 27, and there's no power of x. So 3 to the power of 0 is what we're really dealing with there. And notice we've got 3 to the power of x there, we've added 1x, and here we've got 3 to the power of 2x. Notice from the smallest power to the largest, you've gone up 2x. Sometimes you might see it written like this instead. So e to the x plus 2 equals e to the negative x. This one here is a quadratic because, again, the smallest power is negative x. The biggest power is 2x. That is an increase of 2x. So anytime you see an increase of 2x from the smallest to the largest, this one would have been, by the way, e to the 0, which is a bigger power than negative x. Anytime you see a gap of 2x, you've got a quadratic equation sitting there. And the way we deal with this is by making a simple substitution. We don't want to solve a quadratic and an exponential at the same time, so let's not do that. So first of all, let's remember that 3 to the power of 2x is the same thing as 3 to the x squared. So I can rewrite it like this. And now by letting a simple substitution occur, I can make this a whole lot easier. So let's replace 3 to the x with a. And so we get a squared minus 12 lots of a plus 27 equals 0. And at this point, it's a quadratic we should know from year 10. You may have done this in year 9. And it's a simple solving of quadratics. So that is a minus 3, a minus 9, factors of 27 that add to negative 12. Therefore, a equals 3 and 9. But the question wasn't asking us to solve for a, it was asking for solve for x, and we've made this substitution, this point over here. So what we're going to do now is replace, so we're going to substitute back in a equals 3 to the x. So you end up with 3 to the x equals 3 and 9. Well, that's the same as 3 to the power of 1 and 3 to the power of 2, which means that the only way 3 to the x can be equal to those is if x equals 1 and x equals 2. Last example. This one looks a little bit different. It doesn't look like it's a quadratic, but notice we're different bases. We've got 4 and 2. But also remember that 2 squared gives you 4, and all of a sudden you should hopefully see that our 2 to the power of 2 will appear. So 4 squared we know, so 4 to the x can be written as 2 squared to the power of x. And given that the index laws tell me I can multiply those two, I can actually rearrange that order because remember, multiplication, the order does not matter. So it's 2 to the x, well, with real numbers anyway, minus 4 times 2 to the x minus 5 equals 0. And we're going to perform the same trick we did before. So you're going to let a equal 2 to the x, and it turns it into a simple quadratic. Then we should be able to solve. Factors of -5 that add to 4, well, that's going to be a minus 5, a plus 1. And we're going to be left with a equals -1 and 5. Once again, we are not solving for a, we're solving for x. So we're going to substitute a equals 2 to the x back into our equation. So you're going to have 2 to the x equals -1 and 5. Problem is, you can't have negative. So 2 to the x is always greater than 0. Remember, 2 to the x just means you're doubling every time, or you're every time you increase x by 1, you've doubled. So 2 to the 1, 2 to the 2, 2 to the 3, you're doubling. And if you're going into the negatives, so 2 to the power of -1, you're halving every time. You can never get less than 0. You can't even get 0 with 2 to the x. So we have 2 to the x equals 5. That doesn't work nicely. 2 to the power of some decimal gives you 5. So this is what I'm going to have to write using the same method before now. Log base 2 of 5. And that is the 3 cases of solving exponential equations that you'll need to approach. And I hope that made some sense.